Test. Well, here we go. All right, how's everybody doing? Any questions about the homework or anything else, the class or anything like that? No, it's going great. Everybody understands what's going on. You weren't prepared? Is it one of these? Nine five?
Yeah, 9.5. From alpha 9.5, and then figures C and F. So he told me a reference in another video where he watched about the source of voltage.
Good. I like it when people solve problems on their own. It's good. All right. So which one now? This one?
So literally the last question. What would happen to C and F at the polarity of the switch?
What happens? Note. So this is for what would happen in C and F if the polarity of Vx was switched. Oh, that's easy. So let me sketch that. Well, it's always easy since I know. All right. So let me sketch that circuit real quick. And all I'm going to do is sketch this part of it. And I'm going to flip the polarity of Vx, and I'll switch over here in just a second. So let's sketch the cross-sectional view of the MOSFET. So it looks like this. So this is P plus, and then this is the body connection, which is N plus, and in that circuit I think it was going to VDD. Looking good. Something like that. Okay. And let's just to be safe, let me go back and look. And yeah, so both those two are going to VDD. And then this one goes to a battery, which goes down. Does that make sense? Katie, oh wait, she's not here. So now, what I'm going to do, because I'm learning, is I'm going to sketch the diode on here. Does everybody follow that? Does that look right? Does everybody agree that that's the N well? That's the diode? So if V, does everybody agree that's Vx, so we have it drawn, and the original Vx was the other way? So stare at that for a second. Let me know if you have any questions before we move on. Okay, wait, before I do this, who here has taken, has anybody here taken 421, the digital class? You've taken it, right? So when you took 320, did you cover MOSFETs and the cross-sectional views? Okay.
Yeah, we did. I was in chapter 5, but it was very
Okay. So this is what the cross-sectional view looks like, but you can see the diode. So for this particular one, if this goes more negative, does it do anything? Because normally what you worry about is forward biasing the P plus to N well, but if this goes more negative, what does it do? So let's draw a simplified schematic. So if I drop this node down, what does it do? Well, wait, now I'm getting scared. So when you reduce the pressure here, think of this as a flap. When I teach this, we go over it and we think of this as a flap with a little stopper there. So if you try to move water backwards through the flap, it doesn't. So you're reducing the pressure. You're trying to pull pressure this way. What happens? Yeah, it's gonna shut off, right? It's gonna reverse bias. Does everybody agree with that? So if it reverse biases, it doesn't do anything. You can continue going negative. That's the point. You can go negative here and it doesn't influence. So if you have like an input or you have some signal where it actually needs to go negative, you can't connect it to a source or drain of an NMOS because you then forward bias a diode, but you can connect it to the source, or here the drain of a PMOS, and it won't do anything. And so on the other one, I don't remember what the other problem was, but this is the exact way you approach it. So if you turned in, you had the same thing, but the diode was in this direction, and now you start pulling it negative on this node, it's going to forward bias the diode, and you're going to have problems. Yeah, you're going to get more current, you're going to get more water. Don't think deep. I mean, you think here, okay, if I pull the pressure down here, what happens? The flap can't go back, I don't get any water flow in the pipe. Whereas I increase the pressure here, I can forward bias it. If I drive this node above VDD, it forward biases the diode, and I get water to flow through here, and I don't generally want any forward bias diodes in CMOS. I always want them reverse biased. Yay? Any other questions? Okay, so what I want to do just to start, I want to go over the beta multiplier. So on the quiz on Tuesday, it's going to be something, I haven't made it up yet, I'll make it up tonight or this weekend, that looks like, you know, something where you calculate like maybe this, where you calculate the current that flows, or maybe something like this, and you calculate the current that flows, you know, and then you can mirror it off, whatever. Or I might do a beta multiplier, say here's a beta multiplier, calculate the current that flows, something like that. So there will be a quiz on Tuesday, trust me. And we'll see how that goes. Any questions? So I'm going to rederive the beta multiplier and talk about it one more time. Did anybody use last time's video? I keep wanting you to say no. It really bothers me when you say I used ones from previous years. So I was traveling a couple weeks ago, and I went to update one of my web pages, and it was a super slow internet connection, and I hit publish using Composer, and it was so slow it didn't publish a whole page, so half of it was missing, and I didn't realize that for a few days. So on my site I pay $2 a month to do an automatic backup. So I went online and I said, no problem, I'll just get the last version and pull it up. Well, I go down there and I haven't looked at it like in 6 months. They haven't been doing backups. They didn't tell me, so then I emailed and I'm like, you guys didn't do backups. Oh, we're sorry, the technician's looking at that. So I waited a week. Hey, you guys still haven't got the backup working. So, oh, we're sorry. So last night I got home from travel, I'm like, I got to make sure my website's backed up because I don't have an active backup at home. So I went and checked again. Oh, we're sorry. And I'm like, cancel my backup subscription. So now I'm doing backups of everything, and it takes forever anyway. All right. So you go to all this effort, and then the website goes away. And one time they had a problem, and it basically blew the whole website away. And I started getting all these emails from all over the world, and they were a little bit disrespectful. If you're going to take your stuff off the web, you need to let us know first. I was following this class, and I'm like, I kept getting these emails, and I'm like, what the hell, you know? That's when I put the links in so you could download the videos by connecting to the directory, so they're always watching them online. Anyway. What's that? Yeah. You can go to do a search for the title, and then if you put site :edu, you can pull up the sites that use the book, that listed in the syllabus or whatever. I haven't looked at that in so long. Anyway, so let's sketch the beta multiplier. So I'm going to do this a little bit different, but again, I might ask you a problem on this. I'm going to go into a little bit more depth this time because we're going to use this circuit through the rest of the semester. So I'm going to sketch the PMOS current mirror, and I'm going to sketch this. And what's the point of this circuit? What? It's to make sure that both sides have the same current. So we want both sides to have the same current. Does everybody agree with that? Okay, then I'm going to come over here. I'm going to make my normal size device. So I'm going to ask, before I finish drawing the circuit, does everybody see, I want these to have the same current, but does everybody see why I can't put the gate drain connected device over here and I have to put it on this side for the PMOS? Why? Explain in simple terms why I can't just flip these. What's the problem if I do the following? If I go and I say, what's the problem if I do this?
One that draw one of the devices, so you're connecting to these of the PMOS, the gate of the NOS.
Yeah, so if you think about it, if you do that, then VDD is equal to VSG plus VGS. Does everybody follow that? Well, that's not what I want because then they change directly with VDD, right? Does everybody see that? If I do it this way and I start to increase VDD, the voltage here goes up. I mean, the voltage here stays at VGS, but the drain to source or source to drain voltage goes up, which is fine. I'm just increasing the current, the voltage across that current source. Does everybody see that? So I want this node to stay fixed and not change with VDD. Why do I want that? Yeah, so if VGS is constant, the current stays constant. Does everybody follow? That's the whole point of the beta multiplier, so I can get a current reference that doesn't change with VDD. Questions? So then I'm going to put my resistor here and refresh me. Why do I need to make this guy wider? Tell me in simple terms. What's the deal? Why do I need to make this wider? Yeah, so that the voltage drop across here shrinks. And if I call the current through each side Iref, then I can write VGS1 equals VGS2 plus Iref times R. So if I have that, if I need to make VGS2 small, the way I make it small is I make it wide. Okay, tell me what to do next. So here's the quiz on Tuesday. Closed book, closed notes. Sketch the schematic for the beta multiplier reference and derive the equation showing how the current is determined. Yeah, so would everybody be okay if I skipped a step and I wrote the following? 2 Iref divided by beta sub n plus V threshold n is equal to 2 Iref divided by k times beta sub n plus V threshold n plus Iref R. Okay, how did I get this? And I just solve for VGS. Or I could write this as Iref Tell me if this is right. Yeah, so this has a width of kW. So VGS2 is going to be smaller because I multiplied this up by k. So then when I solve for VGS2, that's how I get this equation here, k times beta. Once. I'm going to be curious how you like the built-in microphone. Go home and listen to it first. Okay, everybody cool? Any questions? You're going to ace the quiz.
We have the two IRS, we're almost right above the line right above the mark. Plus IRS R.
Yep.
Right there.
Yep.
Is that equal IRS R or is it plus IRS? Oh, it's all language.
Yeah, this is plus, plus V threshold in. So I'm going to get rid of those. Then I'm going to divide each side by square root of I ref so that I end up getting square root of 2 over beta sub n equals square root of 2 over k times beta sub n plus the square root of I ref times r. Now key is knowing to divide both sides by the square root of I ref, because if you try to, you can waste some time doing algebra if you do it other ways. Anybody not follow this? So then I'm going to divide both sides by r, and I'm going to move the r inside here, make it an r squared. So I can write 2 over r squared times beta sub n equals square root of 2 over k times beta sub n r squared plus square root of I ref. Yay? And then I can write square root of I ref is equal to the square root of 2 over r squared beta n minus the square root of 2 over k times beta sub n r squared. Just being verbose with the algebra. Tell me what to do next. I don't want to square both sides yet, because then I'd have to cross, or, yeah. Okay, I'm going to do one more minor thing here, but are there any questions about that? No questions? Not being challenged? All right. I want you to show how GM it can be equal to 1 over R. Tell me what to do. K equals 4. I plug that in here. What's 1 over the square root of 4? 1/2. 1 minus 1/2 is 1/2. Squared is 1/4. So then that ends up giving me I ref equals 1 over r squared times 2 times beta sub n. Looking good? But wait a sec. Beta sub n. Or and there's lots of the same terminology over and over again. It's confusing. So everybody cool with this? So I can rewrite 2I ref times beta sub n equals 1 over r squared, or square root of 2I ref times beta sub n equals 1 over r. And of course, what is the square root of 2 times I times beta sub n? Looking good? Okay, so tell me how I use this circuit, and I'm not going to cover the startup circuit again, but that's important. Tell me how I would use this circuit to bias or for a current mirror. Yeah, if I want to do an NMOS current mirror, I'd do this. Mirror the voltage out. It's a current mirror. Does everybody agree with that? If I wanted to do a PMOS current mirror, I'd go do that. Yay or nay?
So the whole circuit is before biasing, it's just a constant current.
Yeah, this is a self-biased reference. And so it's independent of VDD. Once it starts up, it generates a current. That current is somewhat, I'm going to talk about that later today, independent of temperature. But this circuit uses positive feedback. But positive feedback with a gain less than 1 can be stable. Just like if you had a microphone and what's fed back into the microphone, if it's broadcast over a loudspeaker, doesn't screech if what fed back is less and less and less and less. So I want to make sure you understand that. So I'm going to pause for a moment. We're going to intuitively discuss this circuit. And I want to see what happens, okay? So I'm going to break the loop right here, and I want you to tell me, so this is where I want you to pay attention and like look at the circuit and kind of feel what's happening. Don't think math, all right? If I take and I raise this voltage, what happens to the current flowing in here? It increases. Does everybody understand if I turn the faucet on more, I'm going to get more current flowing through here, right? So if I pull more current through this device here, what happens to this voltage and why? So let me ask a simpler question. If I say this is 5 volts and this is 3 volts for some current that flows, and now I increase the current that flows through the resistor, what happens to that voltage? Drops, right? If I pull more water through a small pipe, I get a larger pressure drop. So this drops, say, to 2 or to 1 or whatever. Does everybody agree? So if I increase the water that's flowing in this pipe, what happens to the voltage here? It goes down, and that makes sense because I'm increasing the current that flows in this transistor, and if I increase the current that flows, that means VGS has to go up, and that means this voltage has to drop. Is everybody cool with that? Cool with that? And lead up? Okay. So if I increase the current, then what happens to the current over here? It also goes up, right? And if If it goes up, what happens to this voltage? Wait, if I increase the current that's flowing in this side and it goes through, if I increase the current that's flowing through the resistor, what happens to the voltage here? It goes up. Does everybody see that? Now if I connect this back up, that causes this to go up. But what I'm claiming is that the gain around the loop, even though it goes up, is not going to be greater than 1. If it was 2, this goes up by 1, then it feeds back around, and this goes up by 2, which increases this by 2, then this feeds back around, it goes up by 4, then it feeds back around, this goes up by 8. That doesn't work, right? So I have to make sure what I feed back is smaller than the signal that I have here, so that my positive feedback is less than 1. So I covered a lot of interesting things there. So first off, simple terms. What does it mean by positive feedback? So that means if I go up here and I increase the value, what's fed back is in the same direction. If I talk on the loudspeaker through a microphone, and the sound that comes back through the loudspeaker to the microphone is as loud at the microphone as my voice, or louder, you're going to get screeching, because then it's going to get magnified again and come back around magnified. However, if I talk on the microphone, it comes out, and what hits the speaker is half the volume. Then it'll go and it'll become 1/2, 1/4, 1/8, 1/16, and die out, and I won't get screeching. Does everybody follow that? Okay, that's why I don't put the microphone too close to the loudspeaker. I want my voice to be dominant, not what's fed back from the loudspeaker. Okay, so I need to figure out, so that's what positive feedback means. Gain less than 1 means I come back around and the signal that comes over here is smaller than the one I put in. The voice I talk at this level. When it comes back to the speaker, it's quieter than what it is than what I'm talking. Questions? Okay, so now I want to prove it. I want to take this circuit and I want to prove that the feedback around the loop is less than 1. Okay, any questions? This will lead to a very practical result that you can learn and you can use if you ever decide to use this circuit in your biasing. So here's what I'm going to do. I'm going to do a small signal analysis, and I'm going to use the following. That if I apply a voltage VGS, the small signal current that flows is what? Which equals? Does everybody agree with that? Okay, so I'm going to take this circuit and I'm going to do the following. I'm only going to do AC now. I'm going to apply a test voltage here, our old friend VT. Okay, so first question. If I call this VGS2, does VGS2 equal VTest? No, it does not. But if I call the current that flows in here ID, what can I say about ID? Well, hold on, make it simpler, man. You're getting ahead of me. What is it in terms of VGS2? No, I only ask easy questions, man. What is ID? Here, I'll refresh your memory. Yeah, GM VGS2. Does everybody agree with that? What's the current that flows in R? ID. What's the voltage drop across R? What's that voltage right there? That's right, ID times R. Don't get ahead of me. So now, what is VTest equal to? Everybody agree with that? And would everybody agree that I can write that as ID over GM? And I'm going to be complete and call this GM2. No, because they're going to be the same, because this makes the same current flow. Does everybody agree with that? And so that's ID times 1 over GM2 plus R is V test. What's the current that flows in there? What's the current that flows in there? What's the current that flows in there? So this voltage here, which I'm going to call VGS1, is equal to what? In terms of ID. Alright, we'll write it this. Does everybody agree with that? Or VGS1 equals ID over GM1? Okay, so I'm going to say this is my input and this is my output. I'm going to write the gain as VGS1 over V test. And would everybody agree that is 1 over GM1 divided by 1 over GM2 plus R? And I'm going to tell you right now this is less than 1. You can think about it for a second and convince yourself that has to be, because if 1 over GM is equal to R, or GM1 is equal to 1 over R, which we just derived, this has to be less than 1, but I want to prove it in more detail. Does everybody agree? So this is the gain from here back. It's less than 1. Am I going too slow? Charlie, am I? Oh, wait, he's not here, is he? All right. See, then when you see people, you have to say, hey, he mentioned you in class. Then they're going to be listening for the video. Or do you say my name? All right. So tell me what to do. Input. This is my input and VGS1 is my output. I'm just looking at the loop gain. I want to see if my voice is getting transmitted back to the microphone at the same volume or quieter. So what can I, tell me what to do. Yeah. Well, let me ask you a simple question. Is 1 over GM have units of ohms? What are the units for GM? Amps per volt, right? Or microamps per volt, something like that, right? So does 1 over GM have units of ohms? Yeah. Okay. So now I go and say, well, what is GM1? 1 over GM1, it's 1 over the square root of 2 beta sub n I ref. And what is GM2? It's 1 over the square root of 2 beta sub n times k times I ref. Does everybody agree with that? Well, and if I set it so that 1 over R is equal to 1 over 2 times beta sub n I ref, then I end up getting 1 over, after I cancel everything, 1 over 1 plus the square root of k. Is that less than 1? Yes, it is. If k is 4, that's 1/3. This is an example where positive feedback is good. Yeah, if you're going to try to keep something, well, if you're doing an oscillator, you don't want it less than 1 because then it'll be stable. For an oscillator, you want it to be unstable and to oscillate, so you want your feedback to be greater than 1. Yay?
So what would be a problem that would be greater?
So that's a good question. So let's say, and this actually has happened to people that have, not so much anymore, because on the 3rd edition of the book I went insane about stability and not having problems. But look at the following. What happens if I do the following? Let's say that I zero out. Let's say somehow this capacitor or this resistor becomes 0. This moves towards 1, right? Because this goes away. So it moves very close to 1. So you ask, well, how could you make the resistor go to 0? And this actually has happened. People in industry. They went and they said, I want my reference to be selectable with an external resistor. So they take this resistor and they put it so that it goes off chip. Well, if you put it off chip, it's got a big capacitance, a parasitic capacitance of the bonding pad and everything that shunts it. So if you put a big capacitor across there, it can cause the circuit to become unstable. And that's really easy to show in simulation, so I wanted to show you, okay? Because you're making sure that the gain at some frequencies becomes very close to 1. So let's go look at figure 2024. It didn't make the noise. How random. You know how it's been making the bink and it doesn't work and all that? Alright, so, whoops, let's not use this one. Let's use, where's it? Yeah, we can use this one for now. Oh, spoke too soon. We'll not worry about what this amplifier does in the middle here. I'm going to cover that next. But here I don't have any, actually maybe I can use a different one. Well, anyway, I'll just show you that it becomes unstable. So you see how it's oscillating? That's bad. The way you get around that is you put a capacitance on this V bias N, and I'll cover that more later, or a capacitor here, but the critical one is the V bias N, so that it makes it more stable. And so there you can see once it starts up, now it's nice and stable. Okay. So key point is, if you don't get anything else, you don't want any capacitance across here. Okay? So don't bond out your resistor, because you'd be tempted to, because then you can adjust your bias current externally with a resistor. And people have tried that all the time, but now I've got so much text in the book about how that's bad and positive feedback that I haven't had an email probably in 10 years now. Maybe not that long. All right. So let's go talk about this topology. Are there any questions? So we just did the beta multiplier for long channel, but I want to do it for, I want to show you what happens for short channels. So let's look at figure 2018. And this is the beta multiplier we just talked about, but instead we're using the nanometer devices, a modern process. Okay, does everybody see? Does everybody see the startup circuit in there? So this part, really important, but once it starts up, we don't even pay attention to it. Okay? So this is the beta multiplier, and you understand, oh, there's your PMOS current mirror, forces the same current through each side. There's your device. Notice how it's W is 10, and here W is 2.5, so the K is 4. And then we again have a 150 microamp GM, etc. And we go, and we know if we sweep VDD, which we're going to do now, we want the currents to not change. We want them to be stable. And if you look, that's not good, is it? Currents are not stable. They're changing quite a bit, maybe 50% with changes in VDD. Does everybody see that? The reason for that is the nanometer process have really poor output resistances. So if you look at the curves like from chapter 6 or chapter 9 in the book, and you look at the IV curves, they look like this. You know, they're really slopey, and that's modern process. That's the way they do it. Everything gets smaller and smaller. They still have to make things work. So what if I look at the circuit and I ask, how do I fix this circuit so things don't change with VDD? And the answer is I've got to ensure the drain to source voltages don't change with VDD. So if I look, if I could keep this voltage here at the same voltage as this voltage, the VGSs are fixed or tied. They're not going to vary with VDD. Then I can keep the currents through each side as being the same. So let me show you on the next schematic what I'm doing. So I removed the gate drain connected device here, and then I'm going to put an amplifier in to try to hold these to the same value. And I want to re-sketch that and make sure everybody follows. Any questions? The drain to source voltages are independent of VDD. Remember before I had a gate drain connected device here? So as VDD went up, this voltage was VDD minus the source to gate voltage, changed linearly with VDD. So that causes the voltage across this device to change and thus the currents to change. So let's go take a look and come down here. And then let's go sketch the bottom part of the circuit. Now I'm going to take an amplifier. This amplifier is going to be used to connect or to drive the PMOS and then I'm going to, I want negative feedback, because most of the time when I do amplifier design I use negative feedback. And what I'm going to do is I'm going to, so let me think about this for a moment. Well, let me ask you this. If I ask this impedance here, the R and the K times W over L versus this impedance, which one's going to be bigger, these two or this one? Yeah, the two are going to have a higher impedance. So I'm going to ask you something, and I want you to tell me if you agree. The small signal impedance of this device is 1 over GM. Prove it. You say, oh, well, when he asks me small signal, I write GM. Whoops. If this is VGS, the current that flows through here is ID, which is GM VGS. And that's plus minus. So if I ask, what is the voltage here? VGS. Does everybody agree with that? What's the current that flows through there? ID. So what's the impedance of the device? So that's how I know that this is a 1 over GM. Does everybody agree with that? So if this isn't a triode, it's going to have a much larger impedance than this, but at the bare minimum, this resistance and this resistance are the same if 1 over GM is R. So I want fed back, I want more signal going here and subtracting than I want going to here. So if I pull this node down, these two transistors turn on exactly the same amount. Does everybody agree with that? Because their sources are tied together to VDD. If I pull this down, they turn on, the water starts flowing through both sides, the same exact amount. Which side goes up faster? This side, right? Does everybody agree? Okay, so I want there to be negative feedback to this feeding back here to subtract, so it stabilizes. So I'm going to put this, I want negative feedback is plus and minus, and you go, wait a sec, you want more positive feedback, negative feedback here. Why'd you put the plus terminal there? Just let me pause for a moment. Give me an example of a circuit that employs negative feedback. what's the gain of this, people in 421 lab, or 420 lab? Thank you. Okay, so if this goes up, this signal starts to go up, and then it feeds back around, and then this goes up and subtracts, and this is negative feedback, and keeps the output bounded. So most circuits use negative feedback. Does everybody follow? So here, my feedback to my largest impedance is going to this node, and I'm not connecting it back to the minus terminal. Wait a sec, why? And the answer is, because if I pull this down, that causes this guy to turn on, which causes the voltage here to go up, because the current increases. If it goes up, does everybody agree with that? This node goes up, well, that's going in the opposite direction, negative feedback. So because this is inverting, I get the extra inversion through that transistor. So I'm going to put my plus terminal over here. You have to think about that for a moment. But basically, if this node goes up, then this node goes down. I want to have negative feedback from my highest source. All right. I don't know if that made any sense, but if it doesn't, ask me on Tuesday. Okay? So now, if I've designed this right, this terminal and this terminal will be at the same voltage. They're at the same voltage. These have the same voltage. This has the same voltage, which is equal to VGS. Nothing's going to change here, and my current's going to stay fixed. And then I adjust the voltage here so that the currents are constant on each side. But if you don't believe me, let's go look at the spice. So I put an amplifier in here. I'm faking an amplifier by using a voltage controlled voltage source. I'm going to change that in a moment. And actually, I'm going to make this I'm going to make it only have a gain of 2. So it's not going to have a lot of gain, so it's not going to cause the two currents to be precise and not change. So I want to see what happens then. So you can see they're still changing a bit. Does everybody see that? As I increase the VDD, both currents are still changing. However, if I increase the gain so I get more control, let's say I go to 20, and I hit run. Wow, now they're changing very little, but they're still changing a bit. So I say, okay, well, what happens if I go to a gain of 100? And I hit run. Bam! There it is. Yes?
When you say gain of 100, what does that mean?
Okay, good question. So when I say gain of 100, what does that mean? So let's go look here. So I've got going into my voltage control voltage source. Let's call this V1 and V2. And this has a gain of 100. So the output voltage is then 100 times the voltage on the plus terminal, V1, minus the voltage on the minus terminal, V2. So if I were to model an op-amp, I could use a voltage controlled voltage source and just make this really big number. In fact, that's the way we do it when we're learning op-amps. We fake it. We'll put a voltage controlled voltage source in here and just make this 1,000,000 so that these two have to go to the same value. Does everybody follow? So that's all fine and dandy, but I don't have voltage controlled voltage sources in real life. So I need to have a circuit that I can use for an amplifier. Does everybody understand what I'm trying to do here? Trying to make sure these two voltages are the same, which then means they'll be VGS, so that the currents through each side don't change with changes in VDD. I just showed that that works using a voltage controlled voltage source. Now what I'm going to do is I'm going to replace this circuit with an amplifier, but we're just learning. We don't have that much knowledge of amplifiers at this point. So I need to make one. So that's what I'm going to do. We're going to discuss this. The way I'm going to make it is the following. I'm going to make a put a circuit up here. And what is this circuit called? Aaron. Oh wait, he's not here. Aaron, okay. So what's this circuit called? Yeah, current mirror, right? I'm going to take down here, I'm going to put two devices. Now, let me just tell you, this circuit practically has issues because you can't, unless it's this particular application, these two values will, these two values will drastically change the currents that flow in the circuit. So if in this application, though, they're going to be close to the gate drain connected device current. Does everybody follow? And so I can get away with it, and I'll talk about that more in a moment because it probably made no sense. Okay, so if I ask you the following, and I want you to think, that you know how to answer this. If I drive the current here up, what happens to the current flowing over here? Goes up. What happens to the current flowing here? Goes up. So if it goes up, what happens to the voltage here? If I'm putting more water into the node, what happens? If I'm pushing on the door, what's the pressure going to do? It's going to go up. Does everybody follow that? So I'm going to say this is the positive input of the amplifier. Everybody agree with that? What if I raise this voltage? What does it do to the current flowing in here? Pulls more current. What does it do to the voltage here? If I pull more current out of here, what does it do to the pressure? It goes down. If I'm if I'm pulling more water through something, it's going to reduce the pressure. So here's my shower head. It's coming out. There's my shower head. And there's no water flowing, right? And I ask, what's the pressure there? You say 60 psi. Then I turn the water pressure on. I turn the water, I start to shower. Then I ask, well, now what happens to the water pressure? It drops. And the more water I pull out, the more the pressure is going to drop. If I pull more water out of this node, what happens to the pressure, the voltage? It drops. Does everybody follow? So I can call this the minus terminal. And I can draw the symbol for this as plus, minus, and V out. Here's my V out. This terminal is this. This terminal is this. This terminal is this one. I got to make everything out of transistors and resistors and capacitors. I can't use magical circuits 1 and 2 components, right? I mean, I got to actually make things that people can use. Does everybody see? So let's just, for one more, just to make sure we all follow. If I take this voltage and I drop it, what does it do to this voltage? And I'm skipping the current. And why? What happens to this voltage here? Let's ask Cassandra. Wait, she's not here either. Wait, what the hell? Who else are we missing? Oh, I can think of a couple more people. Okay, what happens to the pressure here if I drop this? If I shut off the water, what happens to the pressure? Goes back up. What happens to the current flowing in this? Decreases. That's a little counterintuitive. You're shutting off the water, so the pressure goes up. You turn the water on, the pressure goes down. Questions? So if this goes up, the current does what? If I drop this down, what happens to the current there? Dane. Oh, wait, Dane's not here either. Damn. It goes down. And then if the current in here goes down, what happens to the current here? It goes down. What happens to the pressure here then? There's no current flowing in there. We remove the current. Assume we keep this turned on the same amount. What happens to the pressure right there? Worku. Oh, damn. I'm going to have to start calling on people that are actually here. So what happens here? If I reduce the water that's flowing, what happens to the pressure? Wait, here's my shower. I start to reduce the water on this side, the amount of water that's coming out. So if I reduce the amount of water here, this guy stays on. What's going to eventually happen to the pressure here? I don't have any water going in. What happens? It's going to drop. Does everybody see that? So the voltage will drop. I reduce the amount of water here. This stays on the same amount. It pulls the pressure down. Does everybody follow that? One more time. Drive this one off. Shut off this valve. Causes the pressure here to go up and the current to decrease. Current decrease causes the current over here to decrease, which means it doesn't have as much strength to pull this node up. So this guy's already pulling some amount down. So then this pressure starts to drop. So wait, this went down, pressure went down. Oh, it's the same direction, so it's positive. This went up, pressure went up, same direction, positive. This goes up, this goes down, this goes down, this goes up. Okay, so please, I'm going to put this circuit in, but what I want you to do is make sure you intuitively understand what I just went through there. And you can look at the circuit, because what I don't want you to do is go on a job interview and then put up a circuit and then you go, where's the equations? I want you to be able to go, okay, well, if this goes up, this is going to turn this, make this pressure go down because I get more current flowing. And I want you to be able to talk through it, not just where's the square law equation and all that, all right? Question?
Just so I understand, when the voltage drops on that, let's go 1, 2, 3, 4, right? The way they put it, all of them before.
So
Yeah,
this-
it'll be NMOS 2, right?
Okay.
So 1, 2, 3, 4. So 1, pull the voltage out of there, you're going to close that NMOS up, which drops the current.
Drops the, yep,
There's no current going through this.
drops the current.
With that, your VD, let's call that VD, right?
Yep,
So your VD is going to, because you're closed off down here, it's going to increase. Because you have a
Yep, that
increase
goes
in
up.
voltage. When you have an increase in voltage, you're going to end up closing that current.
yeah, then the current mirrors over to here because this,
So,
that shuts off, but this one stays on the same amount, so it pulls it down. This is a diff amp,
yeah.
but you generally don't draw them like this. So if this side goes up, this side goes down, this side goes down, this side goes up. This one doesn't swing as much because it's diode connected by this, so it kind of clamps it. This one can swing a lot because it's not got any clamp. I mean, there's nothing clamping it there. The problem with this circuit is in general design is these VGSs, the DC values, if you don't control them well, you're going to have crazy kinds of current flowing in there. And you can do a SIMS and look at it yourself. It works fine in this application because the inputs are always at a VGS. So it just mirrors the current that flows in the beta multiplier. Okay, so let's go put that circuit in and show you. And we'll look at, let's look at 2023. And you can see my here's my startup circuit. Here's the beta multiplier, the 4 transistors. This one's no longer gate drain connected. This one is. I've gate drain connected this one, and I'll just tell you why, and we'll cover it later in the semester. It's easier to compensate circuits, meaning make them stable, if you only have one high impedance node. And the high impedance node is this node right here. Okay? So what are these 4 transistors then? They're the diff amp we just went over. So all I've done, I've removed the gate drain connected transistor here. I've gate drain connected these to try to set them to the same value. Is I've added this amplifier because I want this voltage and this voltage to be the same. So let's see how the performance is. Looks much better, right? If I go now look at the voltages, there's one voltage, and then I'll come over here and look at the other. They're not going to be precisely the same because I don't have infinite gain. If I look at that voltage, oops, they're pretty close. Wouldn't everybody agree? And so the whole point here is that now I'm regulating these two nodes. I can then vary my VDD and my currents won't change much. So it's very robust. Yay or nay? Okay, I got a question for you. Notice that here, these device sizes are 100 or 2.5 micron by 100, or in other words, 50 by 2, if with a scale factor of 50 nanometers. The same size as this one, so I'm mirroring the currents. So these mirror the currents over here. But there's no reason, question? So there's no, notice, because these two inputs go to the same value, even though this guy is tied over here, it's going to go to the same voltage as this. So don't let it confuse you that, oh, I got two devices here. I want the voltage across these two devices. That's how I derive the equations. I want them to be equal to the voltage VGS1 here. So a couple of things. One, if I were to derive the equations governing the operation like I did at the beginning of the lecture today, this circuit, what would I do different? It's a lot more complicated looking circuit. It's exactly the same derivation. There's my VGS1. That should be equal to the voltage across VGS2 plus ID times 5.5K. Notice in order to get 10 microamps, I had to reduce this a little bit because they don't follow the square law. Instead of 6.5, I use 5.5. Next question. If I look at these currents, 10 microamps flowing in each side. So let's look at that. Let's just put a current here. Oops, let's pick the other side. So current flowing into the device is positive. So does everybody see the 10 microamps flowing? Okay, so if I ask now, current flowing in here is what? 10. Current flowing in here, I just plotted 10. What is the current flowing in each of these guys? It's a mirror, mirrors it up, so, and they're the same size, so it's going to be 10. And you can see, hey, it's not exactly 10 because their VDSs are changing, but I mean, it's close. We don't care about them being precisely 10 because we're not mirroring those out. But what would happen if I did the following? Let's say that I made this 5 times smaller, so 500 nano. This is where we use what we covered already. What if I make this 500 nano? Still a current mirror, but what's going to happen to the current that flows here? It's going to drop. It's going to drop by ideally how much? Went from 2.5 to 0.5. 5, right? Instead of having 10 microamps, I'm only going to have 2 microamps flowing in there. What does that do to the gain of this amplifier? If I decrease the current that flows in the amplifier, what do you think happens to the gain? Remember, we covered this. Short question. If I decrease the current, what happens to the gain? GMR out. Remember that plot? Lower current, more gain. No, more gain. Okay, so if I rerun the sim, I look at that. Oops, I don't want to plot that. Let's plot the current that flows in here. There it is. If I rerun and take a mental, with your mind's eye, that picture, I've reduced the size, which lowers the current. Less power dissipation increases the gain. What happens? I can't tell if it's that much difference. But the gain should go up, and it should be flatter, but the scale changed, so can't really say. All right. What is this transistor? Where's the only high impedance known? Meaning only gates and drains connected to it. This one right here. And so later in the semester, we're going to cover stabilizing, and the way I stabilize this is I put a big capacitor to ground, and this way I put the big capacitor to VDD, so if I have noise on VDD, it feeds into this voltage to keep ideally the source to gate voltage constant. Okay, we'll cover all of these things in more detail. But before I stop, are there any questions? Have a good weekend. We'll see you on Tuesday. No questions, huh?